All right, good afternoon. My name is Raymond Miles, and I'm here today from ZT Systems to discuss a server that was shown this morning in Mark Tremblay's keynote. It's also out on display in the Microsoft booth. We're talking about building a solution out of the Project Olympus building blocks. And I'm going to be helped out today by Mark Chubb, who's here at ZT, as well as Scott Ayler from AMD. So, quick agenda here. We're going to hit on our overview of ZT, talk a bit about the actual building blocks that we use to build this system, talk about the specifics of the server, and a few different versions of the server that we built, and then finally, what's the advantage of building product out of building blocks. So, ZT was founded in 1994. It's as small as really as a desktop company. Based in the U.S. We took those roots of consumer PCs and in about 2006, 2007, turned the focus of the company to building servers. And now that's our primary focus today. We are privately held, which is a really lovely advantage for us. We very much focused on doing and working to solve problems of business versus trying to artificially do things for I'll call it equity markets. So it's a really wonderful place to be. We're U.S. based with we have operations around the world. Given our roots in consumer PCs and then growing up into the hyperscale space, we've really molded our entire company after serving the unique customer requirements of hyperscale market, mainly being, I'd call it flexibility of design and flexibility of supply chain. So it's been a really a wonderful journey for us as we've been able to deliver for our customers. We have capabilities for high volume manufacturing, which obviously you need to service the hyperscale market. And we've been involved in Open Compute since 2012 and an official member since 2014 and contributed several designs to the foundation. And with that, I'm going to bring Mark Chubb out on the stage, and he's going to kind of walk through some of the aspects of our design.
All right, thanks, Raymond. So OCP is about, reusing parts that are already made available to everyone. And so we use common terms like building blocks. And so we've been fortunate enough to take a lot of these OCP building blocks and sort of put them together to create additional systems and additional building blocks. So we make use of the motherboards from the Project Olympus hardware building blocks, also the 1 kilowatt three-phase power supplies, and then also in conjunction with the universal PMDU. This is a management PDU that runs vertically on the Project Olympus chassis, and then using a common 19-inch EIA 310 standard, as well as a rack manager. So this is the management part of the PMDU there. So this is the many of you have seen this. This is pretty standard on the OCP website. So this is the full rack here, and then you have some of the building block ingredients here. So you have a compute server, different types of compute servers that ranging Intel, AMD, Cavium, and Qualcomm. These are one-use servers, and then you have a couple of storage JBODs here, as well as a GPU server with an 8-way GPU server. So what we would like to do at ZT is we'd like to sort of add to this list. So as we mentioned, we have the building block ingredients here, and these are what we've done is selected the ones that we're reusing in this 3U server that we've designed. So we've made use of different flavors of this 3U server using Intel and motherboard, AMD EPYC a motherboard. We're using common components like the CPU heatsink, the power supply, the universal PMDU, the rack, and the rack manager. And then we've added components such as the 3U chassis that you'll see, and then PCIe Gen 3 riser cards. We've also added a thermal ducting solution, as well as a power distribution board that sort of merges the power supplies into a common domain. So this is the system here. So as you can see, we sort of take the Project Olympus 1U server, and we sort of build up from there. So this is using the same motherboard and same power supplies, but we're just sort of stacking things up. So in the case of the power supply, you can see that we have 3 of the Project Olympus power supplies stacked up here, and we are load sharing between these 3, running through a common power distribution board, where that distribution board then feeds all of the additional components downstream. So we are using droop sharing, droop load sharing. So this is it's common 12 volt. It's not we don't have separate isolated 12 volt domains for the motherboard or for the GPU cards or for the fans. Everything is joined. So and then we have the PCIe riser cards, which take the by 16 PCIe from the riser slots, and then run that through PCIe switches that then fan out to additional PCIe by 16 slots. We've got 2 different types of, multiple types of risers. Some risers have 96 lane switches that support up to 4 single wide by 16 cards. Or we have some risers that support a 48 lane switch, would support only 2 by 16s, but are spaced out to accommodate double wide PCIe cards. So in the rear, we have dual rotor 60 millimeter fans, and we have 1 fan zone. So so basically everything gets pulled through the common eBay on the on this right side over here, and then on the far left side we have you can't see it. It's a very narrow channel though. We actually have a separate air channel for the power supplies themselves. So, so that the power supplies get their own cooling and their own fan speed. So we have additional room for 2 more fans if needed, and we have a shelf that's in here that is removable for additional customization if you want to put other things in the back. Currently, we just have a hard drive in the back for local storage. And it supports, different Olympus motherboards. So with that, we'll move to the actual picture here, and not a cartoon. So this is the picture of the XPO 200 3U PCI expansion. This is based on an Intel Pearly platform using the NVIDIA P4 cards, GPU cards. And so in this system right now, we actually have 12 of the P4 cards and an additional PCI slot for like a NIC card or whatever you want there. So it's a very IO-rich PCIe expansion box, and this is something that, again, like I said, we've taken all the building blocks that we have from the Project Olympus and sort of just kind of grew it vertically, scaled it up vertically. So so this is the Intel version, and then we have the AMD version. So this is the AMD EPYC processors, dual socket processors with the AMD MI25 GPU. So this system is great for demonstrating the AMD on AMD advantages, and it has demonstrating outstanding flexibility for GPU intensive virtual desktop infrastructure applications, and this. So again, the whole point of this is to show the flexibility of a system like this, being able to sort of drop in different Olympus building block materials. And so with that, I'd like to bring out Scott Ayler from AMD, who is the Vice President GM of the AMD Data Center and Embedded Solutions Group. So.
Yeah, thank you. Thanks so much.
Yep.
Hey, good afternoon. Very exciting to be here with you. And again, for those of you that I haven't had a chance to meet, my name is Scott Ayler. I run the data center business at AMD, and I've been with the company for about the past 5 years. I wanted to kind of open up by telling a story about our story at AMD as it relates to open compute. So we first came into the open compute fold in March of 2017 with Microsoft, in concert with Microsoft around Project Olympus. And we're about now 18 months into that journey of us being part of the open compute family, part of the open compute ecosystem. And you can imagine, as a challenger in this market coming in, what an open standard like OCP does for us. It means that we have the ability to access more systems. We have the ability to access infrastructure based upon a common set of requirements. Now, we love our proprietary hardware. We love kind of the OEM portfolios that we have. But in this market, the ability to drive kind of scale and the ability to easily adopt our technology is paramount. So we're very excited about the progress we've made in the first 18 months with EPYC. Just last week at Microsoft Ignite, you saw Mark Rosanovich, the CTO of Azure, demonstrate on their LV2 instance, running on Microsoft Olympus, world record IOPS performance, 3.7 million IOPS in a 1U server. We also, in concert with Azure, they announced the preview of our HPC instance. So the key thing here is this is not just about kind of at scale, it's also about performance. We're now thinking about, in concert and partnership with ZT, how do we now take this building block that is Olympus and scale it to other use cases in a very simple and very kind of economical and a very fast time to market fashion. And so here we take the goodness that we've established with the existing Olympus infrastructure around EPYC, and we now take and scale that out with a massive number of GPUs. So we now take our AMD EPYC CPUs and pair those with our AMD Radeon Instinct GPUs. And so when you put these two things together, we think it offers a lot of kind of compelling capabilities. First is performance. When you look at what we do from a performance perspective, given our core density, memory bandwidth, and I/O leadership on EPYC, that creates a great foundation for connection to a very large number of GPUs, and we do that with Radeon Instinct. We then take the hardware acceleration features and our SIOV capability in Instinct to give a dramatic amount of performance to our users. So think about the ability in each GPU card to host up to 16 different users. That means in a 1U 2P system, you get 64 users that get kind of a very high level of performance with graphics accelerated processing. Predictability. Looking at what we're able to do, leveraging kind of the hardware capabilities that are built into our GPUs, we now have the ability to have deterministic performance, such that even if you're going into that very large deployment footprint, where you have 64 users at a time, they all have a deterministic level of performance because it's done via hardware. You don't have to worry about software overhead and loading that will drive variations in performance like our competitor. Security. Has this been the year of security or what? Right? When you look at Spectre, when you look at Meltdown, when you look at Foreshadow, security is definitely top of mind. And for those that kind of don't remember, AMD's not affected in terms of the Foreshadow and Meltdown vulnerability. So if you're paying 5 to 50% performance hit with Intel, please think again. Please come see us. But we do have great security features beyond that. So we have secure encrypted virtualization that couples with our hardware-based VDI controls, which make for less attack vectors in software. And what this means is that we now, in a very kind of rapid time-to-market fashion, through partnership of leveraging existing building blocks like you've seen with ZT, is we now have the ability to get a very substantial TCO savings in a fairly rapid period of time. So think about greater than a 22% TCO savings is what people are seeing with this platform. The other side benefit is our GPUs actually do not carry end-user licensing fees. So you do not have to pay an end-user license fees with Radeon Instinct. So the combination of those two things are really driving very substantial TCO savings for our customers. So when you look at The XPO200 3U series from ZT, it's a great instantiation of what's great about the open systems that AMD is helping build with EPYC and Radeon Instinct, but also a great example of how do we think about bringing innovations into the market as a challenger in a very rapid and fast time to market. I'll turn it back to Ray.
Thanks, Scott. All right, well, thanks, Scott. Yeah, it's been really just a great partnership with AMD as we've worked on this system and are bringing it to market. So just to kind of in summary here, just want to just reconfigure. I mean, touch base again on the advantages of this development model, right? So the whole idea is that the building blocks are known good hardware components, right? And what we're doing is trying to configure new solutions out of those, that foundation. And both the hardware and the firmware, because the firmware is super important as you look at configuring these systems. So again, having those to start with as the framework for this new system was really, really a big advantage. Not only from a time perspective, but also from a an NRE and development perspective, right? We were able to not have to go develop our own motherboard and not our own heatsink and PDU and rack. All that stuff is already done. We just pull those components and then focus our development on the net new pieces to deliver this powerful PCI expansion system. And again, it's just and then our focus was on the targeted pieces, right? We needed to develop a new riser card, so we were focused our hardware resources on the signal integrity required, the simulations, the tuning and whatnot on those new components. While we took the marrying of the other components and then validated the whole system. So again, that targeted development helps to ultimately lower development costs and improve time to market and deliver new solutions out into the marketplace. So it's honestly kind of the whole vision of Open Compute, right? Is to take these pieces and develop net new, fast and really cost efficient and the right solution, right? As we know, I mean, this cloud market requires the right hardware, right? And having the building blocks has helped us to do that. So that's the end. Thank you so much for your time. Yeah, there is some time for questions. If there's any questions, we could probably take a few. I don't know if there are any, but we're happy to do that. Oh, that's right. Yeah, and oh, by the way, we are our hardware is actually out there in B1. If you want to go look at these two systems, they're sitting there. I guess we answered all their questions.
All right, great. Well, I think we'll be around afterwards if you have any that you'd like to follow up with.
All right, thank you.
Thank you.
Okay, thank you.